So, hello everyone. Welcome to the third live session on this course on microsensors and nanosensors. Grossly, we have around four questions, and we will try to take them one by one. Okay, so let me take the first question. The question says that why were we using Doppler frequency? Okay, basically the student is trying to understand that although we are in the microwave motion sensor, why we are still using Doppler effect, basically. Okay, so let us try to understand the concept of Doppler effect. We all are aware of the basic effect, but then I will try to a little bit mold it towards the motion sensors. Okay. Then the question was, second question was, what is the piezoresistive meaning? So we'll try to take this question and the surface reflectivity on the optical displacement sensors, and then what are the challenges in the microsensors and nanosensors, particularly when you talk about the scalability of the, fabrication point of view. The student is trying to understand that what are the challenges when you try to scale up these microsensors and nanosensors. So give me a moment. I will connect. So we are pausing for a minute and I will resume. So sorry for the delay. Let's start discussing each problem one by one. The first one was why were we using the Doppler's frequency, and we'll try to first understand the Doppler effect and then try to mold it towards the motion sensors. Okay. This question, as I have mentioned, is in terms of occupation and motion sensors. Okay. So we know that the Doppler frequency, or basically the shift, Doppler shift, refers to the change in the frequency of a wave due to the relative motion between the source and the observer. Okay. And basically, this effect is mostly understood, or this shift is mostly understood in terms of the sound effect. Okay, but this is possible. The Doppler shift is possible for sound. It is also possible in the light, and it is also possible in microwave and radio waves. Okay. So if you talk about any electrical sensor or say optical sensor, you want certain change. So you want that, say, if the input is changing, okay, the transfer characteristic of the instrument or the device should shift. Okay. So basically, what this Doppler effect does is it helps you in understanding the movement of the object with respect to sensor. Okay, so we have discussed this ultrasonic occupancies sensor in detail, and what I will try to do is I will try to just overview this so that you are more connected to this, or you will understand this effect of Dopplers, particularly not only in ultrasonic, but as well as in the microwave also. Okay. So in the ultrasonic occupancy or motion sensor, we have discussed that these waves are acoustic waves with frequency, say anything above the human hearing capacity. Okay, so anything like 20 kilohertz or so. Okay. So when these waves is incident on an object, a portion of their energy is reflected back. Okay. So I mean, mostly it is diffusive in nature. So regardless of the direction from which the energy comes, it is basically reflected uniformly over a wide solid angle. It can be even 180 degree. Okay. So if an object is in motion, the frequency of the reflected wave will differ from the transmitted wave, definitely, because a portion is getting absorbed. Okay, this is known as the Doppler's effect, and this effect refers to the apparent change in the frequency of the wave resulting from the relative motion between the source of the sound and the observer. Here, the observer is nothing but your sensor. Okay. So the frequency in the Doppler's effect can be simply determined by this particular equation. I think we have discussed this frequency in detail in our motion sensor lectures. Okay, so in this equation, basically this F naught. Let me take the pen. So this frequency was F bar was basically observed frequency at the sensor. Okay. This V naught, Vs are the velocity of sound wave in the medium, velocity of the observer if you are observing at a certain speed. Okay, and the source velocity. Okay. We have taken certain convention to understand these frequencies. Okay. So we have seen that if the source or the object which we try to detect is moving towards the observer, say you have deployed certain sensor at rest, because of the Doppler's effect, what is happening, the frequency that you are obtaining is basically V by V minus Vs. Here V naught, I'm taking it as a 0, because if you see, V naught was the velocity of the observer, and I have just mentioned that your sensor is basically at rest. Okay, so V naught is basically 0, and the source is moving, which is the object basically. So you are getting this frequency as V by V minus Vs. Okay, into the, of course, the frequency. Okay, the actual frequency. Now, if say you are not deploying or if you are not using the Doppler's effect, okay, so if you are not using the Doppler's effect, what you will basically will have that the source you will if you are not quantifying it using Doppler's effect, I hope that I have understand this question. Okay, so if you are not using the Doppler's effect, the source is moving towards you, so it will be really difficult to quantify that because you are using it for motion detection. So you may be visibly you can say that the object is moving towards you, but then it is not always possible, particularly without using the Doppler's effect. Okay, so this effect is basically very much important for knowing the status of the object by using their velocities and the actual frequency. Okay, so as I have mentioned that the definition of sensor itself was like you want to measure certain changes, and yeah, that has to be, of course, in electrical parameter that a transducer can do. Okay, but the frequency shift or frequency changes is what the Doppler's effect gives to you. Okay, there can be other cases also, like if the source is moving away from the observer, then you have this kind of the change of frequency can be given by this. Okay, so the idea is very simple. You had a transmitter which emits certain pulses, in this case, say ultrasonic pulses, then receiver read the reflected signal, and there are provision to compare these patterns to obtain the actual frequency. Basically, when an object moves towards the sensor, the reflected sound wave's frequency is increasing, while basically the wave is compressed. Basically, the wavelength is decreasing. Okay. Similarly, when it is moving away, the frequency is decreasing, or you can say that the wave is stretched. Okay. Now, as I have mentioned that this Doppler effect can also be extended to microwave signals. Okay, so if you remember, the microwave motion sensors were working on the similar principle, where electromagnetic waves are backscattered or say reflected by the object, whose size are comparable or even larger than the wavelength of the incident signal. Okay, now the reflected waves are either detected, then it is amplified, and these signals are further analyzed. Okay, the distance to an object is measured by the time delay between the transmitted signal and the reflected signal, while the object's speed is determined from the frequency shift of the reflected wave. And when you talk about this frequency shift, again, you are basically using the Doppler's effect, right? So when you try to utilize it for the speed measurement of the object, which is the essential use of the microwave motion sensor, basically you are utilizing the Doppler's effect. Okay. So here it should be noted that the microwave detectors belong to the category of radar, which we all know what it is in basic terms. Okay, so these microwaves that we are using for motion detector, we have seen that they are long enough to pass easily through most of the contaminants in air, be it cloud or be it dust, and they are short enough to be reflected by the larger objects which we want to detect. Okay, the basic construction was something like this, where you had an antenna, a gun oscillator. What is a gun oscillator? We have seen The amplifier, and then frequency meter, which basically is detecting the Doppler's frequency, right? The gun oscillator, we have already seen that it is used to generate microwave RF signal in case of the microwave motion sensors without needing a conventional resonant circuit, while the oscillator in this case generates electromagnetic waves at say certain frequency, say f0, which is the actual frequency that you have seen in case of ultrasonic motion sensors. Okay, so a part of this oscillator frequency f0 is passed through the iris into the waveguide and then focused on the antenna. This directs the radiation towards the target object, and the antenna transmission frequency is related to the wavelength by simple frequency equation like f0 is equal to c0 by lambda naught, where c0 was the speed of light in air. Okay, so the target is moving, say, away at a certain velocity v, the reflected frequency will decrease, okay, and it will increase for target which is approaching the antenna, okay, and this we have seen in case of the Doppler effect. Okay, although the effect was initially, as I have mentioned, was discovered for the sound, it well applied for electromagnetic radiation and the other, like I have mentioned, for other rays. Like, okay, for sound waves, the propagation speed can vary depending on the movement of the sound source, while for electromagnetic wave, it always travel at the speed of light, which is the constant and is independent of the light source movement in any media. Okay, so the frequency of the reflected electromagnetic wave can be estimated using the special theory of relativity as something like this. Right, Fr is equal to f0 into root 1 minus v by c0 square by 1 plus v by c0, where v is the actual speed of the object which is under observation. Now, be it whatever, okay, the speed of this v, the object will be always, say, much lesser as compared to c0. We know that this c0 is of the order of 3 into 10 power 8 meter per second, right? So whatever will be the speed of this this v of the object, okay, it will of course be a slow moving object as compared to the light. Okay, so practically for any object, the term v by c0 and the term v by c0 square is very, very small as compared to the value 1. Okay, so this value can easily be ignored, and this simplification makes the equation for the reflected wave frequency identical to that we have used for acoustic wave, which is Fr equal to f0 by into 1 by 1 plus v by c0. Okay, so if you use the f0 value as we have seen some time back as f0, this f0 value as c0 by lambda naught, you will essentially reach at the point of the Doppler's equation that we have utilized in case of acoustic sensors. Okay, so basically, you are reaching to the point where the microwave motion sensor also rely upon the Doppler's effect. Okay, so that's why I mentioned that both kind of sensor, be it acoustic motion sensor or microwave motion sensor, both is highly dependent or is basically based on the Doppler's effect, right? So now I will skip these slides because we have already discussed this in detail. Okay, so I hope that the concept of Doppler effect is clear to you, and how this Doppler effect, I mean, how the say two different sensors that we have seen, say acoustic or say ultrasound based motion sensor and microwave motion sensor, how they are basically based on the Doppler's effect is clear to you. Okay, now second question was what is the piezoresistive meaning. Okay, so the meaning of the piezoresistive or piezoresistivity, and the student has found this word in the, I think this accelerometer is from module 9 or 10. Okay, but if you check your course, in 7th module we have discussed about this piezoresistive force sensors. Okay, the concept of piezoresistive force sensors are actually in this module we have talked about piezoresistive materials in detail, and again in this module 10 where we discuss this accelerometer, there also we have used the same concept of the piezoresistivity. Okay, so what I will do is I will try to explain this piezoresistivity once again in term of force sensors, and then we'll come back to the piezoresistive accelerometers. I think that will give you more clarity about these piezoresistive materials, okay, and what this is all about. Okay, so piezoresistive force sensor, if you remember, are the most common method that we have, because these are naturally force sensitive materials. We have seen that this is most common method for microforce measurement, and it offers a direct conversion of mechanical deformation to electrical signals. Okay. Now, these sensors were based on the piezoresistive effect. Okay, so when a metal or a semiconductor material is subjected to certain kind of stress, its resistance changes in proportion to the deformation. Okay, and this is exactly what the piezoresistive effect means. Okay, so when you have a material, be it a metal or be it semiconductor, like silicon itself has a very good piezoresistive property. Okay, so when you have this kind of piezoresistive material, when you subject it to certain kind of stress, its resistance changes. Okay, and this resistance change is mostly in proportional to the deformation that you apply. Okay, so this effect basically is different from piezoelectric effect. Okay, so do not get confused between piezoresistivity and piezoelectricity. Okay, both are a little different. Okay, recall that the piezoelectric effects generated a charge or voltage when you squeeze it. Okay, there were polarization, and because of that there were charge separation and there were a voltage generation. Okay, so but this piezoresistivity is about a change in the resistance, as the name also suggests. Okay, so do not get confused between piezoelectricity and the piezoresistivity. Okay, so stress deforms the material's crystal lattice, and this deformation alters the mobility and the concentration of charge carriers. And we know that these directly influence the electrical resistance of the material, and that's how the deformation alters indirectly the electrical resistance of the material, even by altering the mobility and the concentration of charge carriers, right? So primarily semiconductors like silicon, germanium, some metals like iron, copper, certain polymers like polyaniline, polypyrrole, they were showing certain piezoresistive properties, and exactly why they are used in piezoresistive force sensors. Even the polysilicon has a very good piezoresistivity property, and to quantify that, we have seen this particular equation where this delta RS by RS, which is basically the resistance variation of the strain gauge due to deformation divided by the resistance of the strain gauge before deformation, was equal to the strain factor multiplied by the strain, which is basically length variation of the strain gauge due to deformation divided by the length of the strain gauge before deformation for a piezoresistive force sensor. Okay, so you can use it for quantification of the change in the resistance properties with respect to the deformation. Okay, so we have used it at various positions by doping or forming piezoresistors in silicon, or by doing micro machining. So we have seen a number of piezoresistive force sensors, like simple bulk silicon do possess the piezoresistive property. So we have seen bulk silicon piezoresistive force sensor. We can use MEMS based, or we have developed MEMS based piezoresistive sensors for the polymer based piezoresistive materials. We also had seen the flexible polymer based sensors, right? So if you remember, the bulk silicon piezoresistive force sensors were looking something like this, where you had the piezoresistor directly fabricated in a bulk silicon. So bulk silicon uses the substrate itself as the sensing material in this case, and then you have diffused regions aligned in a specific crystallographic direction for maximum sensitivity that acts on the piezoresistor. So we had this kind of arrangement to collect the change in the resistance of this material. Okay. Similarly, for the MEMS-based piezoresistive force sensor, we have seen this kind of arrangement where we have seen the fabrication on top surface of the silicon wafer by surface micro machining. Okay. Then also we had seen for flexible polymer based piezoresistive sensor, where you had a flexible polymer on top, while the piezoresistor is sandwiched between a conductive layer and a flexible polymer, and then of course everything was placed on a polymer substrate. Okay, so this kind of arrangement was there for measuring the change in the resistance of the piezoresistors, right? Similarly, this we discussed in week 7. Then in week 10, where we discussed about piezoresistive accelerometers. So the concept of piezoresistivity remains same. Okay, but the detection technique of this type of accelerometer is change in the resistivity of the piezoresistive material. So there we were using it for force detection. Here we have modified the structure a little bit, and then of course using proof mass and other things, we are using it for the application of accelerometer. Okay, this change of the resistance is mostly caused by the mechanical strain due to the acceleration forces that we apply on the accelerometer. Okay, so the piezoresistive accelerometer incorporates a strain gauge as a sensing element that measures the strain in the mass supporting spring. Okay. The strain can be directly related to the magnitude and the rate of the mass displacement, and of course, subsequently with an acceleration. Okay, so this was kind of structure for our piezoresistive accelerometer. This was the inertial mass, and the gauge is basically the piezoresistive element. Okay, so the microsensor was fabricated in a 3-layer of silicon, something like this. Okay. The inner layer, or we called it the core layer, consists of the inertial mass, okay, and the elastic hinge. The mass is suspended inside an etched rim on the hinge, with the piezoresistive gauges positioned on either side for the measurement of any change in the resistance. Okay, the gauge detect motion about the hinge. The outer 2 layers, this base and the lid one, are fixed. When acceleration is applied along the sensitive axis, the inertial mass moves around the hinge, and the recesses are made in base and lid to allow movement in the inertial mass freely by doing certain kind of dry etching. Okay. And now the gauges on both sides of hinge allow detection of movement of the mass by getting deformed themselves. Okay, so actually when acceleration is applied along the sensitive axis, the inertial mass rotates around the hinge, and this will create a compressive stress on one gauge and tensile tensile stress on the other gauge. Okay, so since gauges are very short in nature, even a small displacement produces a large resistance changes in these piezo resistors. Okay, so we have seen that there were various schemes to trim down the zero balance and other things. Will not go in detail of that, but that is how the piezoresistive accelerometer worked. Okay, so you had piezoresistive gauges, and they are used in this particular fashion. Okay. We have seen a number of advantages of this piezoresistive accelerometer, like they have very good sensitivity, they can operate in a wide temperature ranges. They are suitable for both low to medium frequency applications, and the power consumptions were also not very high. Okay. So this is, I think, the concept of piezoresistive accelerometer, or in general, the concept of piezoresistive materials or piezoresistive effect, and then how this piezoresistive effect can be efficiently utilized in development of sensors. And at least we have discussed two different sensors, like one is for detection of micro forces and another for detection of minute accelerations. Okay. Then next question was, what is the meaning of surface reflectivity? And this we have used this term in case of optical displacement sensor, particularly in the limitation. And we discussed that this optical displacement sensors are very much sensitive to surface reflectivity. And then let us right now discuss this in detail, that how these optical displacement sensors are sensitive to surface reflectivity. And I think by that it will be more clear that what I mean by the surface reflectivity. Okay, so but before I jump into the optical displacement sensor, let me first define the surface reflectivity in mathematically, and then we will go towards the concept of optical displacement sensors. Okay. So the surface reflectivity of a material is quantitatively defined as the ratio of the intensity of the reflected light from the surface to the intensity of the incident light. Of course, this is defined at a certain value of wavelength and also at a certain angle of incidence. So basically, it is I reflected by I incident when the angle of incidence is fixed, and say wavelength is also fixed. Okay, so when you change the wavelength, the surface reflectivity will also change. Okay. So now let's talk about the optical displacement sensor basic construction. Okay, so an optical displacement sensor usually require, or position sensor will require at least three components: a light source, a detector, and a light guiding device, which may include certain lenses, mirrors, or fibers. Okay, and of course, the fourth component, which is not part of this position sensor or displacement sensor, but we are talking about it, is the object which we want to detect. Okay, although it is not a part of this optical sensor or optical displacement sensor, but this is a very important entity because we are trying to detect this particular object. Okay. So we have seen a number of optical displacement sensors, like one was like laser displacement sensor, confocal displacement sensor, time of flight sensor, laser Doppler vibratometers, or say vibrometers, and interferometric sensor. We have seen a number of optical displacement sensor. I will just take an example of, say, first one, say laser displacement sensors. Okay, the idea of this triangulation sensor or laser displacement sensor was like by projecting a laser beam onto an object, okay, then detect the reflected light, say this is the object and it is reflected, and this reflected light is detected by a CMOS sensor, say at a certain angle. Okay, now the angle of the reflected light combined with the known geometry of the sensor measure the distance of the object. So please note here a term called geometry of the sensor. Okay, so the geometry will also include the surface roughness and other things in the object. So let's see what is the impact of different surfaces on it. Okay, so impact of different surfaces is like how much light is reflected back to sensor. A high reflective surface will reflect a strong signal, and a dark surface will absorb most of the light and reflect a weaker signal. Okay, so if the when I say high reflective surface means the reflectivity or surface reflectivity of this surface is high. Okay, so the reflected signal will be considered as a strong signal, while with the weak surface with a weak surface reflectivity, it will be considered as a dark or say not reflecting surface. Okay. So the angle of the reflected light combined with the known geometry, so if a sensor is not calibrated, say for a specific surface, a high reflective surface can be misinterpreted as object being closed because the signal that you are receiving is a strong signal. So the sensor may read that, okay, the object is nearby, or say vice versa. Like it can consider it consider it as as something which is at far if the signal is weak, although the object is very near, but the signal is very weak because it is reflecting poorly. Okay, so that is the concept of basically the surface reflectivity. If the surface reflectivity is poor, okay, there is always a chance of creating error. So in both the cases, basically, you need calibration. So the object which you want to detect, so before you actually deploy your sensor, you should have idea about its surface and its surface reflectivity. Okay. So that is the concept of surface reflectivity. Okay. Now, the final question was, what would be the challenges in realization in terms of the scalability of the microsensors and the nanosensors? Okay. So if I talk about the challenges for the scale up production of these sensors, there are many. Okay, if I talk, the first challenge can be the initial fabrication cost and the complexity required in the fabrication of these sensors. So initially you have to put money heavily for the say if it is a microsensor, you should have a simple at least class 1000 clean room, and then you should have say a number of at least a line of lithography, starting from say wafer cleaning to say etching. Then if you talk about deposition system, you should have, we have seen that there are n number of films required, be it insulating, be it conducting, be it say semiconducting. You need n number of films in these microsensors and nanosensors. Okay, and then you heavily rely upon number of characterization. So along with this fabrication technology, you should also have a line of characterization techniques. So this this pile up in the cost of the initial setup. Okay, so the fabrication cost initially is high. Then initially you will see that this yield is not that much. So low throughput is something with which initial sensor production or when you try to scale it up, this can be another challenges. Okay. Then the material that is basically your receptor. Say if you talk about a simple chemical sensor, okay. I mean, fabricating same receptor every time, that will be a challenge. Okay, so there is a great variation if your process differs slightly. Also, there is the quality of the receptor changes heavily. Okay, so the defects in the receptor is something which is very challenging to control when you talk at the micro and nano level. Okay. Then integration of these devices and packaging in a miniaturized packaging systems is another challenge, because particularly for the MEMS devices where you have the movable parts. Okay, so the scale up idea of this MEMS devices is a little challenging, because then you have to ensure the quality. Okay. Then long and short-term stability and durability of these microsensors and nanosensors are challenging. Okay, the noise is another factor which challenges the scalability of the devices. And then all these sensors that we have discussed, most of them require calibration. Okay, so then calibrating these devices are again challenges. Okay, then we have seen the, certain sensors like for some, say, certain healthcare kind of devices. Okay, so then they pose a good amount of regulatory and ethical challenges. Okay, you have to take permissions. Okay, because you are calibrating it against the standard devices which is already in place. Okay, so there you have to have things fixed for you should be able to answer the regulatory and other ethical challenges. Okay, and then the final is of course the economic barrier. Okay, so these were some questions that was posted. Okay, so I think that we have discussed them in more detail. Then there are certain questions on this page. Let me take some of them. Okay. So there are some questions online. Let me take some of them. Okay. What will be the difficulty of the final exam? Okay. So don't worry, the exam is like any other exam. Okay. If you have gone through all the modules and you have also followed the assignments, okay, I hope that you will be able to answer most of the questions. The paper is definitely not that difficult and will not be anything out of syllabus. Okay, so don't worry much about, don't stress yourself. Okay. Then next question is, what percentage of questions can be expected from the assignment? You can expect maybe around 10-15% questions from the assignment, or near to the questions of assignment. But I mean, there are certain standards of NPTEL you can also find for other courses. We follow the same pattern. There is no such changes in the pattern of that. Okay. You want to know about the one student has posted that he or she wants to know about the paper pattern. Okay. There is no as such any pattern of the paper. It's objective in nature. One should that is one thing. And the I think weightage for all the modules are equal. So you cannot think that this module will have more weightage or this module is not that important. It's not like that. Okay. So all the modules have kind of equal weightage, so you can prepare like that. Okay, I was not able to complete all the assignment. Will that have an impact on my score? And another student has told that I have completed a 9 out of 12 assignments, so it's a very good score if you have completed 9 out of 12 assignments. Okay. So don't worry much. There might be certain penalty for not completing assignment and all. But if you score good enough in the end sem, I think that will, I mean, those things can be taken care. Okay, so you will be able to manage those gaps. Okay. So the NPTEL follow certain pattern for the assignment, and of course it carries some weightage. Okay, but you have not completed, so that's fine. You should not worry. You should more focus on the end semester exam now. Okay. So I hope that there are no more questions. Okay. I wish you best of luck for your end semester examination. Okay, and thank you. Thank you for attending this session. I hope that the discussion was helpful for most of you, and particularly those students who have posted the questions. I was able to clear their doubts.